pretty easy to figure out. They were all 0, just as we should expect, right?
Right.
But if we do the expansion on this column, or even more so, if we do it along this bottom row, right? That was the suggestion. Then we don't even have to do the work of computing the determinants.
So what is the expansion, what is it describing to us about this matrix or this system? What information does it lead us into?
Yeah. So that's sort of the topic for today that I haven't completely gotten through yet. The only thing that we've talked about so far is that it tells us whether or not the matrix is invertible.
The cofactor expansion.
The cofactor expansion is this is just a way of computing what the determinant is. So the determinant is just a special number that describes the matrix.
Right.
The only thing that we know so far about that description is that if it's 0, then the matrix is not invertible. If it's non-zero, then the matrix is invertible. But there are lots of other things besides that.
Okay.
So one thing that we saw, and we're going to run out of time before I can get to this, an explanation of this. But one thing that we saw is that when we did these row operations, when we took a multiple of this row and added it to this row or to this row, or we took a multiple of this row and added it to this row, these types of row operations, I can't remember, we had a special name for those. Replacement, something like that. I think that was what it was called, replacement. So let's write that down. Maybe it's not totally obvious from the example that we worked here, but that replacement didn't change the determinant, right? We knew it wasn't going to change it because the determinant was 0, and the row operations don't change whether or not a matrix is invertible, right? So we knew that it had to be 0 because we knew this matrix was, the determinant of this one was 0. So it's not invertible. So all of these row operations aren't going to change if it's invertible, which means the determinant still has to be 0. So it's kind of easy to see in that case. What we'll see, what you can see in general, and you'll have to read the proof at the end of the section we're going through this, is that replacement does not, in general, in any case, when we take a replacement of one row and we use it, a multiple of it, to add or subtract from another row, that replacement does not change the determinant. So if we start from a matrix A, and I'm going to use this kind of...
Is that just row replacement doesn't change the determinant, or is there some sort of other thing we need to use to replace?
We'll write row above this. We only really talk about row operations. That's the only kind of operations that we've talked about on matrices so far. And so, replace sim. Nobody said anything. Replacement. Okay, that's a real word. Row replacement does not change the determinant. Yeah, this is those 3 operations that we talked about that maintain row equivalence at the very beginning of the semester. So we're going a little way back. Like I said, I can keep harping on this all day. The concepts that we learned on day 1 are going to continue to be applicable all the way to the end of the semester. So we can never forget those. Row replacement does not change the determinant. So if we go from matrix A to matrix B by row replacement, then let's continue to use this absolute value symbol. The determinant of A is equal to the determinant of B. So the determinant does not change. What does this tell us? If a matrix, how can I say this? Well, I guess just like this. Let's continue through this without expanding on this one. The next one. What do we call it? Row interchange or row transposition? Which one was it? Interchange, okay, thank you. So row, interchange. What should we call this? Row interchange. I want to say it multiplies the determinant by -1. This is just sort of a shorthand way of saying it. Row interchange makes the determinant negative. So what do I mean by this? More clearly, if I go from matrix A to matrix B by an interchange, so if we interchange two rows, then the determinant, I keep using this, the determinant of B is equal to negative the determinant of A. So it swaps the sign. If one is negative, then the other one is positive. So, coming back to your question from earlier, what happens if we interchange this row at the bottom with the row at the top? We would have, it would have made it negative, but
Any row swapping makes it negative?
any row swapping, we do one interchange of a pair of rows. We pick two rows and we swap them. Yes?
Is that rule like an extension of the fact that we have like signs to each?
That's a very sort of clear way to see why that's happening, right? So if we do the cofactor expansion, the signs that will appear in front of those factors, these factors are here. If we swap those two rows, then, well, it's clear if we swap this row and this row, because the positives will become negatives and negatives will become positive. It's not quite so clear if we swap two positive rows. What happens is that because this row is, let's see, how can I explain this? The sign change sort of gets moved into the submatrix itself. So yeah. It's not so obvious why that happens, but if you kind of chase down the details, and there is a proof in the book. Unfortunately, we don't have time today to talk about it. 3, is this one? Yes. So this one, is it called scaling, row scaling? You seem to remember the names of these.
Yeah, it's good.
These names, replacement, interchange, and scaling, these are the basic row operations. The book gives them names. In general, I've never seen specific names always applied in the same way to these in the literature. So I don't remember what they are. But row scaling, let's just say row scaling scales the determinant. Okay, so that's a shorthand way of saying what it does. What does this mean? More specifically, if we get from matrix A to matrix B by taking one particular row and scaling it by some multiple k. I'm going to have to write a k here to indicate how much I'm scaling it by. So if I replace one of the rows in here with k times that row in here, then the determinant, I did it again, determinant of B, I might as well write it. These are completely equivalent notations. The determinant we can think of as a function that takes in a matrix and spits out a number. The determinant of B is equal to k times the determinant of A. So whatever that scaling was of the row, then the determinant will be multiple of that. Let's do a sort of what if here, a counterfactual. And let's replace this entry by 1. So now we no longer have this nice property that this bottom row is all zeros and we get a 0 for the determinant. Oh, we got 4 minutes left. I don't have time for this example. I'm sorry. Try this out for yourself. You'll see that if we had done the complete row reduction, where we end up with a 1, a 1, and a 1 here, well, when we did the cofactor expansion, we would have ended up getting 1 times 1 times 1. It was something that we kind of tried to slip into the end of last class, which was that if you have a triangular matrix, its determinant is equal to the product of the entries along the diagonal, right? And that comes from the cofactor expansion. We expand here, and then everything else is zero. So we go over here, we expand by here, and then everything else is zero. And then we go to here, and it's just this number. We end up getting this times this times this. And so if we scaled this so that this was a 1, we would have been scaling the determinant by 1/3 of its value, negative 1/3 of its value. So to undo that and get the actual determinant, we would have to multiply by -3. So that's where that scaling comes in. Now these are really useful for determining actually what a determinant is. We get this special rule because we can always do these interchanges and replacements to get a triangular matrix. And we know the determinant is the product of the entries on the diagonal. So let's say that the determinant of A is equal to, I'm going to say sum, either positive or negative, 1 times the product, how do they write this in the book? Product of the pivots. I'm just going to write this in parentheses. Whatever the product of the pivots is. So whatever those are going to be, those are going to be maintained through this process of here we go. Here, we found the pivot, 1, -3, 0. And this plus or minus 1 is going to correspond to how many times we had to do transpositions. So R is interchanges. So we get this property. We also have, and this is stated as a theorem in the book, a square matrix is invertible if and only if its determinant is not equal to 0. But like I said, when we first started talking about determinants, we can think of the determinant as a number with that property. It's a number that tells us, we can compute it from these row reductions. And it tells us whether or not the matrix is invertible, because if it's 0, we would end up dividing by 0. Now, squeezing in the very last few seconds of the class, 2 very important things. 1, the determinant of A transpose is equal to the determinant of A. If you took a matrix and you swapped it along the diagonal, you did the transpose, you flipped it like this, what you'll see is that the cofactor expansion gives you the exact same number, right? Now, instead of, as James was saying, now instead of multiplying, things that are in rows, you do the transpose and they're in columns. So now we can think of that, we do that operation, but we do it to the whole matrix. So instead of going along a row, now we go along a column. If we did the transpose, we could have thought of that as going along a row. But now those entries are transposed just the way that you were saying before. So this is true. And now the most important and fascinating one of them all, the determinant of A times B is completely unexpected from the formula for cofactor expansion. You never would have guessed this just by looking at the formula. This is true. Determinant of A